So, as a continuation of what I did in the earlier session on lattices, we will do some aspects of structure of crystals. As I told you in the earlier context, logically speaking, lattice plus basis equal to structure. See, this is that logical relation. Lattice is a mathematical concept which say involves spatial rhythms, as we have seen, and basis is purely physical. It is in the form of atoms or molecules, and so this means if atoms or molecules are accommodated according to a specific mathematical model of spatial rhythms, you will get a crystal structure. That is what this tells you. Okay, this is mathematical and this is physical, atoms or molecules. Physical, and so you have here physical thing. Okay. So, now of course, the atoms or molecules, see atoms are so simple and even molecules, okay, in the usually encountered structures involved in solid state physics, the molecules are simpler. Okay. But because of the fact that the lattice can be quite complicated, the structure can be complicated. Within the limited time available for us, what I will do is I will concentrate my attention on some very popular crystals. I will take up diamond for example. Examples are diamond, that is carbon in the diamond form, silicon, germanium. There are some other crystals also which I will take up after this is done. Okay. Now, today in the forenoon session, I have harped on the intimate relation between a cube and octahedron. We have seen that in a cube the fourfold or C4 axis is more spectacular, while in the octahedron it is the C3 or threefold axis which is spectacular. Okay. These things play a rather complementary role to each other. Now, there is a very famous figure called tetrahedron. Meaning is quite clear, tetra means 4. So, this is a polyhedron having 4 faces, each in the form of an equilateral triangle. So, one can draw the tetrahedron in 2 ways. The best way to understand a tetrahedron is take up an equilateral triangle, take its centroid which is somewhere here, then you just go this way either this way or that way. In the opposite direction, I will go this way, say perpendicular to the plane of the triangle passing through the centroid. You will develop a triangular pyramid. Okay. Then say this is A, B, C. AB equal to BC equal to CA. If I go this way, suppose this is O, OA will be equal to OB equal to OC because of the fact that I am going through the perpendicular to the triangle passing through the centroid. But when a particular stage is reached, I stop such that, suppose this point is O, OA equal to AB, then what will happen? AB equal to BC equal to CA equal to OA equal to OB equal to OC. You will get a special case of a triangular pyramid called tetrahedron, and because of the fact that it is difficult to draw it say in that fashion, what I will do is I will slightly change perspective and put it like this: A, B, C. See, instead of this thing, this equilateral triangle, I have slightly, by changing perspective, I have shown it like this. Then this is the centroid and perpendicular to the triangle, and say going through a straight line passing through the centroid, I reach the point D. Okay, so you have, see, okay, ABCD is the tetrahedron. Okay, one can imagine this to be the tetrahedron. It is a figure bounded by 4 equilateral triangles ABC, ABD, okay, ACD and BCD, 4 equilateral triangles. Okay, so you are quite, right now we are quite friendly with the with the tetrahedron. Okay, again, now what I am going to do is to negotiate kind of marriage between this tetrahedron and a cube. Okay, cube we are quite friendly with, already we have done it in the morning earlier session. Yes, this is a cube. This is the octahedron, sorry, this is the tetrahedron, ABCD is the tetrahedron and this is the cube. Well, I ask the question, are they compatible? Most probable answer from the students will be certainly no sir, they look quite disparate. No relation or no congruence between these two figures, which are quite dissimilar, widely dissimilar. But a closer perusal will tell you that in fact these two people are kind of wedded to each other, they are made for each other, they can be so, say, one can easily accommodate the personality of the other, as we are going to see. The secret is, I will call it S4, it is a code name, it is S4, improper fourfold axis. I will explain what is meant by S4. I will apply S4, that is improper fourfold axis, to a cube. See, let us take any vertex for that matter. I have chosen this vertex of the cube. In the earlier session, I told you that C4 involves rotation through 90 degrees because repeated 4 times you go to full circle after say in C4. Okay. Now, S4 means improper fourfold axis, that is S4 involves S4 equal to C4 followed by a reflection in a plane perpendicular to the concerned axis. This is the description of S4. Let us apply it. See, I am going to show you that if you apply this to this, you will get this. Apparently, they are quite disparate. Nobody will believe that this has anything to do with this, but in fact, this has very much to do with this. This can be comfortably accommodated inside the cube. I am going to apply S4. Rotate through 90 degrees. See, because 4 times repeated full circle means rotation is 90 degrees. You rotate through 90 degrees about this axis. See, the axis can be like this, or it can be like this, or it can be like this, all passing through the body center of the cube. So, let me for convenience take up this axis, rotation axis, C4 axis along this direction passing through the body center. Apply C4, this point goes to, see, this is C4, C4 twice, C4 thrice, C4 4 times. You are back home, full circle is negotiated. So, C4 means that will take this to this 90 degrees. Immediately reflect it in a plane perpendicular to this axis. This is that axis, so the plane perpendicular is like this, and so C4, then sigma, that is reflection in a plane, that will map it to this one. See, C4, then reflection, it is reflected in a plane like this. So, A goes to B. Now, you yourself can do it, just repeat it. See, another S4, that means C4 followed by sigma, C4, then sigma means reflection, it goes up, see, you will reach this point. Now, once more, C4, okay, sigma D. Now, if you do it once more, C4, see, all C4 means rotation about an axis like this. Okay. So, C4 will take it to this point, then reflect. You are back home in A. Now, we join, see, these points. Okay. See, consider the dotted figure A, B, C, D. Evidently, it is a tetrahedron. A, B, C, D is a tetrahedron. It is precisely this. See, the solid figure is the cube, the dotted figure is this tetrahedron inscribed inside the cube. So, the tetrahedron can easily be or comfortably be accommodated inside the cube by the prescription S4, which is C4 followed by sigma. Well, these are typical group theoretical symbols. Okay. Yes. Now, you are very close to diamond structure, because let us join the body center of the cube from here to OA, OB, OC, OD. This is O, the body center of the cube. OA, OB, OC, OD are the so called tetrahedral, say they make tetrahedral angle. One can easily identify that OA, OB, OC, OD are respectively along the 4 body diagonals of the cube. Okay. So, and another thing which is very crucial here is that in negotiating a tetrahedron inside a cube, one has suppressed the center of inversion associated with a cube. See, in a cube, if A is a vertex, its diametrically opposite vertex, okay, is A prime. A and A prime are of equal status inside the cube. Similarly, B and its diametrically opposite point B prime. B prime. See, these are diametrically opposite points, they are of equal status. C and C prime, D and D prime. See, there are 4 body diagonals of the cube, A prime, B prime, C prime, D prime. They say are all having equal status, and again A and A prime are having equal status inside the cube. Similarly, B and B prime, C and C prime, D and D prime. But look at the tetrahedron. A is part of the tetrahedron, but its diametrically opposite point A prime is not part of the tetrahedron. Say, I will say A is in, A prime is out. Similarly, B is in, it is part of the tetrahedron, B prime is out. C is in, C prime is out, D is in, D prime is out. The primed vertices are now rejected. The unprimed vertices are accepted, they are part of the tetrahedron. The primed vertices are not part of the tetrahedron. So, what I have done is, in accommodating the tetrahedron inscribed inside the cube by the application of S4, I have suppressed the center of inversion associated with a cube. In other words, I will say that while the cube has a center of inversion, namely the body center, the tetrahedron does not have that center of inversion. The center of inversion is suppressed inside the tetrahedron. Okay. Now, see, so that OA is half of A prime. So, evidently, OA is along one of the 4 body diagonals of the cube. Similarly, OB is half of B prime. So, it is along the next body diagonal. Similarly, is OC and similarly is OD. In other words, OA, OB, OC, OD are along the 4 body diagonals of the cube. And so, these body diagonals of the cube, one can simply calculate, okay, by taking the direction cosines of these say lines. One can calculate the angle. It is a very interesting angle, 109 degrees, 109 degrees 28 minutes. It is a very famous angle called the tetrahedral angle. It is the angle between the sp3 hybridized orbitals, okay, which is that angle is very famous in organic chemistry, because organic chemistry say entertains say sp3 hybridized orbitals in carbon compounds. So, OA, OB, OC, OD are say directions making an angle 109 degrees 28 minutes. Now, so this is the story of the tetrahedron inscribed inside the cube, and the prescription, the catchword is S4, improper fourfold axis. Our next task is to negotiate the diamond structure, because now we are very close to the diamond structure. See, I will say that diamond structure is such that inside the cube you have a super tetrahedron, a tetrahedron which say can accommodate 4 tetrahedra. That is the diamond structure. Okay. Of course, often in the textbooks one will see a statement that a diamond structure is say it involves an FCC lattice with a diatomic basis, okay, such that if one atom, carbon atom is at 0, 0, 0, the other is at 1/4, 1/4, 1/4. That statement is perfectly okay, but it can best be understood in terms of this, that is in terms of the tetrahedron inscribed inside the cube. So, our next task is to redraw this in the form of the diamond structure. See, what my strategy is to accommodate a tetrahedron along OA, another along OB, a third one along OC and a fourth one along OD. That is the diamond structure. Let us see. So, now at this stage of our discussion, we are fully convinced that after all the cube and the tetrahedron are not disparate, they are quite congruent, they are quite they can blend with each other so easily, okay, and that is what we have seen.